Bienvenidos todos, enseguida comenzamos.
Just trying to use the microphone. The people listening from home can listen. Well done.
Bueno, ready. Bueno, pues buenas tardes a todos, a todas. Muchas gracias por su asistencia. Pues es un gusto para nosotros tenerlos aquí el día de hoy. Quisiera iniciar agradeciendo a la Facultad de Ingeniería de la UNAM, a la División de Ingeniería Civil y Geomática, perdónenme, por la hospitalidad y por habernos permitido organizar este evento de manera conjunta, también al Instituto de Ingeniería de la UNAM y obviamente a la Sociedad Mexicana de Ingeniería Sísmica, que bueno, hicieron posible esta conferencia. Me da mucho gusto presentarles al profesor Stefano Pampanin, que es una persona muy reconocida a nivel mundial sobre temas de ingeniería sísmica, sistemas prefabricados y rehabilitación estructural. Él es un profesor profesor titular de Ingeniería Estructural en la Universidad La Sapienza de Roma, Italia, desde 2014, donde ha sido profesor de Diseño Estructural, Ingeniería Sísmica y presidente del Clúster Estructural y Geotécnico del Departamento de Ingeniería Civil y Recursos Naturales, también en la Universidad de Canterbury, Christchurch, Nueva Zelanda, en donde también trabajó desde 2002 y bueno, sigue trabajando, colaborando actualmente también. Ha sido presidente de la Sociedad Neozelandesa de Ingeniería Sísmica de 2012 a 2014, donde fue nombrado miembro fellow en 2017. Recibió el título de ingeniero civil en la Universidad de Pavia, en Italia, y el grado de maestro en ingeniería en la Universidad de California, en San Diego, y el doctorado en el Politécnico de Milán. Es miembro de varias asociaciones gremiales en Estados Unidos, Europa y Japón, y ha recibido numerosos reconocimientos internacionales por sus contribuciones, principalmente en el área de estructuras prefabricadas. En los últimos 25 años ha dedicado esfuerzos a la investigación y desarrollo, tanto experimentales como numéricos, para la reglamentación e implementación práctica de soluciones innovadoras en el diseño sísmico de sistemas estructurales de concreto reforzado y madera de bajo daño, que es de lo que nos va a presentar el día de hoy, así como para la evaluación sísmica y rehabilitación de estructuras existentes. Pues por favor ayúdenme a agradecerle con un fuerte aplauso al doctor. Thank you very much.
Thank you very much, Professor Guerrero, Hector, and for everyone, thank you for the UNAM University, local university, which is one of the largest, not in Mexico, you should know, but around the world. I come from Sapienza, which is 120,000 students, and we claim that we are the largest university in Europe. You are three times as big as us. So without saying things which can go in different direction, I would like to give my best wishes to a professor which is here in the audience. So I'm very pleased to see Professor Sergio, I thought about it because we say Sergio Alcocer, with best wishes to be able to come to Europe with a different title and tell us what is happening with your potentially new role as a rector of this university. Because it would be nice to see a civil engineering and earthquake engineering expert talking about the governance of university. Having said that, it's a great pleasure to be here. Potrei parlare italiano e voi potreste capire. I could speak Italian, you would understand, but let's use the broken English. And if we are using the broken English, which is our common international language now, I would like to share an experience, no more than that. It's not a lecture. It's a sharing an experience, and it's an experience which unfortunately happens to be a common problem all around the world. The topic, the title is the same title that I've been given at the keynote lecture at the Mexican Society of Engineering. And again, thanks Professor Guerrero on behalf of the society as a president of that who kindly invited me to share this knowledge. It was impressive to see how Mexico, the country, and I understood that also Mexico sometimes is considered a city, is actually facing the same challenges, but it's actually finding interesting solutions. So I will be really looking forward to go back to my country and pass on what I've learned, and hopefully there will be some way of high-level collaboration down to the detail level of collaboration. Here you see the problem for earthquake engineering, but let's say for the society around the world. The target of the discussion of today is how can we go towards an earthquake-proof building. So the title, I maintain the title, I did not have the time to change, but I actually changed the slide, because we are moving towards an earthquake-proof building, which means that we don't have an earthquake-proof building. And this is something important we need to tell to the society. We do not have an earthquake-proof building, and we are just looking, I see that is actually for volume, asking for volume. We are looking to develop something, because we can't afford, obviously, to have a building collapsing and killing people. That's quite obvious. We achieved a technology capable of protecting lives, and this is not known by people, but we need to make one step forward, which is a big, big challenge. The step forward is talking about resilience in the way that people would understand. So talking about the possibility to not go down deep in the hole and then taking too much time to raise up, because we want to avoid a big hole as an impact, such that we can get out of the hole very simply. And you will excuse me if I would be using non-hysteretic rules in this presentation, no formulas of shear, no torsions, no dynamics, but I will be talking the earthquake engineering for decision makers, the earthquake engineering for stakeholders. If we are not able to get out of our comfort zone, which is the bonding reinforced concrete, the beam column joints, which I like to test in the lab, and raising our discussion to a political level, unfortunately, that changes in the impact of seismic risk reduction is not going to happen. So what we need to discuss is what means resilience from our point of view. It's not about a fuzzy word. It's actually something that we need to measure. If we cannot measure something, we cannot monitor that something. If we cannot have a target measurable in the years, we cannot have a time frame. We cannot have basically a plan to achieve something. And this is, if you wish, the most important things that we should be doing today is while we are communicating a seismic risk problem, we have to find solutions, we have to find a plan, and we too have to convey things which are in the words of everyone, in sort of a normal discussion of non-technical people, including life cycle analysis, circular economy, sustainability. And while I'm using the hands in such a way, which is typical of the Italian way of talking, in New Zealand that would have been forbidden. I learned 16 years in New Zealand that my speech should have been with my hands down and not moving too much my head, just being very, very dry and it's a different culture, and I learned a lot from them, which I brought back to Italy, and I would explain what was the exchange of information. When you're talking about sustainability, I give you a trick. So I give you insights of something which became a scientific trick to manage, to convince people that seismic resilience should be on the top of our priority everywhere in the world, including central northern part of Europe, so I'm conflicted, whereby they talk about Green Deal, European Green Deal. You know the European Green Deal? It's the target of, against climate change, we are going to make buildings and city energy efficiency. We are going to make a big rehabilitation in terms of energy efficiency of building. So, considering that high priority, those countries, I'm exaggerating, I need to be careful because there are people from, I don't know who from is connected from home, with those countries complaining all the time, like Italy, Greece, in Europe, about seismic, they should be lining up with our targets, which is climate change, and I totally agree. I so much totally agree that we managed in our research team to demonstrate that if you're really targeting sustainability, and sustainability now can be measured rightly or wrongly using a social pillar, an economical pillar, and an environmental pillar. There are three pillars, which are now somehow into in an algorithm, into a scheme which can be measurable with weights. You can put the weights that you wish, but there are ways of doing it. So if it is true, and you, whoever you are telling me that sustainability is the priority in the world now, and I would totally agree, let me explain that by looking at cycle analysis of a building, and it happens to be that that building is in Mexico, is in Chile, is in California, is in Italy, is in Greece, is in Japan, is in New Zealand, is in any part of the yellow dots of this country, it happens to be that there are quite a number of millions of people living in those unfortunate seismic regions. If I take into account the cyclic of life of a building, and it does happen that there is a probability of occurrence of the earthquake during the lifetime, and we know that very much. So it's a matter of 10% in 50 years, 2% in 50 years, 5% of 50 years. It's a matter of there will be earthquakes during the lifetime of the structure, damaging my building. We never thought in the earthquake engineering community that is not only a part of damage, losses. We know a lot of things now. We think we know a lot of things. Losses, damage, downtime. There's much more than that. What is the cost in terms of CO2 and energy, direct energy, to repair my building? Wow, you got a point? Suddenly, I'm talking sustainability language. I'm talking about how much it will cost in terms of CO2 during the life cycle of a structure. If I happen to be unlucky to live in a country which is a seismic-prone country, how will be my CO2 emissions, which is not only the embodied energy and the operational energy, is actually the repairing CO2 and energy, direct energy cost of my building. Suddenly, Italy goes into the high top ranking of sustainability needs in Europe. You can imagine that when I had this discussion in some political environments, people were not very happy to hear that suddenly we have a mathematical solutions or expression or evidence to actually, let's say, change, if you wish, the ranking of priorities due to climate change. Because we are actually looking at sustainability in the way of, I don't want to spend CO2 and direct energy to repair my building. So let's go through and try to see if we have solutions, not for retrofitting buildings only, but actually to start from new. At least every single new building will have to have, and let's now say in a proper way. I would try to avoid to talk about should be seismic safe, because seismic safe is not enough in the brain of many people. I would say it should be the most sustainable building, because the most sustainable building will be done in a material, in a design way, in a repairable form, in a, you see the point, resilient way, which is going to be the most sustainable. So it's just a matter of turning the point, changing the point of view. To share the knowledge, I need to drive you through a little bit of a free trip. We start from Italy, we go to New Zealand, we go back to California. We have a stop by in Mexico, and then we are going to Chile, and then we are going back to Italy, then we go to Japan, and then, so we keep on moving through the highway of troubles. These yellow dots, I like to call them the highways of troubles. You go to New Zealand and need to go fast and quick. It's a high seismic country. High seismic doesn't mean necessarily high risk. High seismic means that the virus that the patient buildings are going to be subject to is very high. But if the patients are far away from the virus, or the patients are young enough, it's more likely than not that the risk of that patient to die is lower than an old patient designed according to pre-codes, which means basically a genetically weakened building, genetically weakened patient, which can suffer a big threat of life just because of a flu. Let me rephrase it. Who told you that the risk is higher in the yellow dots? Of course, given the same building, if you are in the yellow dots, you're at higher risk. But in principle, you can be at higher risk in a place where the seismicity is not very high, it's like a flu, but the vulnerability of a building is very high. So clearly enough, you start engaging the whole world saying, are you sure that your gravity load-bearing design buildings, no seismic design according to the British standard anywhere in the world, for example, in some places called Australia, are at less risk than something that everyone will know, Japan? And so you're starting entering into a concept of combination of the virus intensity with the patient vulnerability, which is much different than what people think. So in New Zealand, the earthquake intensity is the magnitude that we are talking about is 8. 7, 7.5, 7.8, 8, 8.2, and so forth. And luckily enough, the big ones are actually following this area of literally movement between plates. It does exist. The plate movement that you've been studying at school, at primary school, they do exist. So fast and quick, the problem of risk is if you're finding an earthquake finds the patient to kill, which means buildings, which means people. Luckily enough, New Zealand does not have a high density of population, which is not the story of Italy, which is not the story of Mexico, right? So in Mexico and Italy, we have a high density people. In Mexico and Italy, we have a high density construction. In Mexico and Italy, we have older, genetically weakened type of buildings. So it doesn't take an earthquake engineer to understand that the risk in our country is very high. But if we are talking about seismic risk, this will not be, in Italian we say the movente. This will not be the sufficient reason for which there will be an implementation of a seismic risk reduction. It's incredible to say. But nowhere in the world the people started typically a massive plan for seismic risk reduction because of the earthquake risk, before the earthquake. After the earthquake happens, there is a massive amount of repairing just around that. And while I'm repairing, obviously, Mexico City in 1985, while I'm repairing and I'm reconstructing a city, of course, I'm doing something better. But did you see in your country, just I'm talking about my country in Italy, after the earthquake in L'Aquila 2009, a major effort in some other cities than L'Aquila? Did you see in Mexico a major effort in Guadalajara reconstruction or strengthening buildings after the Mexico City one? I don't know. I'm just asking. Why did not happen? Because the virus did not hit, and so there was no feeling of a need for a medicine. Let's go to New Zealand. I don't have the time, but I will please ask you to go back and see what was the Christchurch earthquake sequence in 2010 and 2011, because it was a massive novelty in the earthquake engineering community. The earthquake was meant to come from the main fault, but the earthquake decided not to read the code and not to actually start the bomb, the earthquake failure from the main fault. It just happened in another fault, which was a big one, 7.1 magnitude, 35 kilometers of distance, but not the major fault. After 6 months, not happy of having done just quite a major failure, but no victims after this earthquake for a number of reasons. After that, 6 months later, there is an aftershock, which is it had a very important intensity. The magnitude of that was 6.2. Why are people, including journalists, media, who are actually spreading the knowledge in sometimes not probably the best way because they don't have the time to study, why are they thinking that the magnitude earthquake means a high risk? So magnitude 8 earthquake means high risk. No, I told you again. It's a matter of seismic intensity to me. So if I have a magnitude 8 at 100 kilometers of distance, 300 kilometers of distance, 500 kilometers of distance, magnitude 9, I care less than having a small earthquake close to my eye. The reason for which I'm using the eye is that it's a vulnerable building. Everyone will not be happy to have something exploding. It's very small, very tiny, these fireworks, a small firework that you were playing when you were a kid nearby your eye, because vulnerability and intensity and shaking is going to give me the risk. So this is completely changing what people understood about earthquake magnitude. And when you hear people saying the earthquake in Japan was magnitude 9, that earthquake would have destroyed complete Italy, would have been like Atlantis, this type of science fiction thing. And you're wondering, no, what are you talking about? The earthquake in Japan, it's magnitude 9, totally agree, but it's very often coming from the subduction zone, which is 100 kilometers from the city, and they have actually 45 seconds at least of time whereby my colleagues are receiving an alarm, whereby hotels are actually saying 45, 44, it's a countdown that gives you the time. And I was very pleased to hear from Professor Guerrero today that after your Mexico City earthquake, the Mexico in 1985 one, basically you had implemented alarms around the city because you have time enough, approximately 40 seconds, 1 minute, to get that alarm. In some places, you don't have that time. So if there was an earthquake like this one here nearby the city, there is absolutely no time to be advised, no early warning whatsoever. So Going quickly, today we have to discuss about low damage technology, earthquake-proof building, but let's understand what is the earthquake risk of those buildings. You know, because you are either students or researchers or younger researchers or senior researchers, professors, engineers, so you are here because you are dealing with earthquakes from the engineering point of view. And so you will know that we are dealing with earthquakes, thinking that that mathematical expression, which has been somehow developed by George Hausner, by taking the El Centro record 1940 and by shaping El Centro signature into a spectra. There was a shape which basically is the shape that we are using everywhere around the world. We forgot that that mathematical shape is not a earthquake signature. It is an envelope of many earthquakes, an average if you wish, a percentile. If you stay in that city for hundreds of thousands of years and you're waiting for all the bombs to explode, and you make basically an average, an envelope or probability of exceedance in the lifetime of your structure. So a single earthquake, the one that is going possibly to destroy our life, will not be spectral compatible. Let me rephrase it. The code is using a mathematical expression, which is an extremely advanced way for us to understand what can happen, but the single event will not be following mathematically the full code spectrum. There will be ups and downs. If you're lucky, you'll be on a low. If you're unlucky, you'll be on a high. What is the problem? If it's a new design building, let's say now in a different way, the robustness, the resilience of the detailing is sufficient enough to be able to go through many cycles, even to take a bigger intensity shock, means a big punch, a bigger than design one. But if you're dealing with existing buildings, they do not have that resilience inside. So the existing buildings are actually genetically weakened because they are not able to take something different, higher than what they were designed for. So we have a problem. The other problem is that's already well known. We were talking forces, but the earthquake don't speak in forces, speaks in acceleration, displacements, and in velocity. So we learned that it would be appropriate to work in terms of displacements. And displacements are the ones that are going to crack a wall, are going to create a flexural shear failure, flexural shear interaction. Truly enough, the brittle behaviors are more force-dependent, but drift and forces, so displacement and forces, can be a good way, the combination of the two, to deal with earthquakes. Guess what? 1974, Freeman was already introducing the capacity spectrum approach, non-linear pushover into an acceleration displacement response spectrum, 1974, becoming 1990 the capacity spectrum. So we are in 2000 and, looks like a TV show, we are in 2023, so 50 years later, we are still trying to convince us, colleagues, that we should be doing a nonlinear static analysis. Incredible. So let me try to ask, don't reply, think in your brain. You already knew how to do a pushover before ever starting any course in earthquake engineering. And you knew it because when you were doing your section analysis, and if you're young or if you're old, you were either using an allowable stress approach, and then you've been told it doesn't work. You cannot just have an elastic or brittle behavior and just blind yourself hoping that the post-elastic will be good. You must switch to limit state design. A limit state design that you've been learning in Concrete 101, Structure Design 101, no seismic whatsoever consideration, is actually telling you was the reason for which we banned stress, allowable stress, because it was a way to say, if I want to understand and control the plastic mechanism, the failure, I will have to see it, and then I will come back. That moment curvature is a pushover. You were doing a pushover without knowing it. So why people, us, I'm talking to the engineers at home, are complaining that these academics are pushing for pushover? You're pushing for pushovers. That's actually a quite nice one. We were already doing a pushover by hand in a moment curvature. So let's just go back to the nonlinear analysis by hand. And that's exactly what we've been developing in New Zealand, a pushover by hand, which is called SLAMA, Simple Lateral Analysis Mechanism, which I don't have the time. But if I had a little bit of few hours, you would be brainwashed so well, because I can do it, such that you will be not brainwashed only, but you will have also competence to be able to do a pushover by hand, and you will not be paying any more software fee, which the software houses are not very happy when I say that, or you will be doing your own analysis, as a good engineer should do, before starting user, the fast computer, to give you an answer. What is this doing with our earthquake proof? I'm going to get there. Tom Poli was saying something fantastic. Easy, simple, important. Professor Thomas Poli. You know Park and Poli from New Zealand, Professor Robert Park, Professor Thomas Poli. It's incredible because it's a different world. I had the great honor to have Nigel Priestley, their PhD student at that time, as my co-supervisor with Michele Calvi. I was in Pavia, Milan, and then San Diego most of the time with Nigel Priestley. And when I met Professor Tom Poli, I understood why Nigel Priestley was so great, because his mentors, Park and Poli, were unbelievably great. So, apart from the fact that Thomas Poli was Tom and Robert Park was Bob, and I could not just make it from an Italian approach to call them Bob and Tom. It looks like a cartoon, Bob and Tom. I'm Bob, I'm Tom, okay, nice to meet you. But I just can't really physically do it. And then I managed. He was saying something simple, and for me it's everything. The earthquake does not read the code means the earthquake will not be the one that you design it for. Means the code provisions are not the one that the code is going to respect. The level of intensity is not the one that the code is going to do. You cannot tell an earthquake, could you please slow down, because I actually designed for a PGA of 0.2 and you are coming with a 0.5. So it would be quite nice to find a technology in the future to slow down earthquakes. I'm saying something which will happen. Some way of damping in the soil the earthquake waves before they come to us. It will happen, because there is already some thinking, but at this stage there's not. So also in New Zealand, where capacity design, hierarchy of strength principles have been developed in the 60s and then implemented in the 70s everywhere around the world, also in New Zealand, prior to that knowledge, building did not know about capacity design. And so there were weak columns and strong beams. There were soft story mechanism. This is actually quite a well-designed building with a tower in a way, but it did collapse during the earthquake, like others. And towers collapsing, or towers, five-story building, collapsing in New Zealand, they created quite a number of troubles. The earthquake that I'm referring to is the aftershock. This is the before and after. Before is the city. After, people thought this was pollution. There's no such a pollution in New Zealand. This is actually the debris coming out of the collapse of a city. The city center collapsing. Remember, this is 6 months after the main shock. The main shock has already filtered the main killer buildings. So problems, I already saw it, 90s, the 60s, 70s, 80s, and now we are going to the 80s. So this is one of the best examples of precast concrete. I've been using this picture, this photo, which also comes from Jose Restrepo PhD thesis work and many other people working on emulative precast approach. Mario Rodriguez, I'm very pleased, thank you, Professor Rodriguez, for being here. We were seeing each other now at the conference. We were saying 2001, FIB meeting, 2002, in Yucatan, Playa del Carmen. And I made a joke saying, were you there? Of course, I was organizing it. So Professor Rodriguez was actually the convener of that workshop in Mexico when we were discussing about precast, seismic design of precast. But before the 2002, in 2000, we were together on the building San Francisco, which was going up using new things than this. Anyway, excellent solution for emulative approach. You emulate concrete, you get the concrete behavior. And this is, let me introduce to you, let me do a little bit of the television show. Let me introduce to you the best ever seen plastic hinge in the real world. This is the best ever seen plastic hinge, which means you need a strong earthquake, which is hitting hard a well-designed building. And he's actually showing to you what you have been seeing in the lab, but this is the real world. This real world is telling you that there is a fantastic beam weak strong column mechanism, weak beam strong column. So there's a plastic hinge here protecting the column, which is the leg. So the building stands up. The building had plastic hinges all the way all the way up the floor, and they are the sacrificial fuses. There is a problem though. And now, as soon as I show this thing, you understand what is the problem. We did not explain to people that this is absolutely normal, like it would be normal for a car to save the pilot, but not to save itself. So there was a missing link in the communication because people thought that an earthquake-resistant building is actually earthquake-proof. So of course, it will not look like a car. Why it will not look like a car? And so we are now trying to explain to people that what you get from the code is what you get from a car safety design. So the car safety design is plastic behavior to protect plastic behavior, beautiful plastic behavior. You know it all from these things. People did not get it. We did not explain to them. Thanks to this fantastic sacrificial fuse, you're going to demolish your building. And there will be half of the city which is going to be demolished because, of course, when you crash the car at this stage, you don't expect the panel beater to be able to fix it, right? You're simply going to your insurance and asking for the car, and the day after, 2 days after, you're going to get a car. There was a problem. We did not think that after something like this, we would have been given back the buildings. We didn't think we would have been given back the city. So let me just stay on that. We went through now the ditch. We are not talking about building killing people by collapsing. We are talking about new design, well-designed building which are protecting the lives. What can we do better? Because this is not sufficient enough. And how much is becoming, how much greedy are we becoming? We were protecting lives when buildings were collapsing, so we managed to do that step, and now we're saying it's not enough. Life safety should not be the minimum target. Sorry, should be at least the minimum target, but not enough as the target, because saying that the buildings did what they were meant to do is good for us, but people are not happy. And we also didn't know. You tell me if we, structural engineering community, are actually able to do the calculation of structural design 101 in a 102 course, when instead of starting from your section analysis approach, you're actually starting from a damaged building. Do you have a course on damaged building structural design? Or do you have a course of deteriorated, corroded bars, buildings, so things which are real in the real life, and what is the moment curvature of that? The theory is being developed, but we don't have it that yet. So we did not know. We cut and crane a portion of the buildings. We brought into the lab. It took quite an effort to test how many cycles that plastic hinge could have taken. And I don't tell you the good news or the bad news. I'm referring especially to the young researchers that I see. Just go and see in the literature what were the results of that. We are hardly able to repair a building because after you yield the steel, you don't unyield the steel by just injecting grout. Let me say it again. After you develop cancer into your own body, it's not just by covering the wounds that you are going to stop it. And this is the same thing for corrosion in a way. So something that we need to understand, but the reality was, second city in New Zealand. New Zealand is a small country, I take it, but this is the second city in New Zealand, 450,000 people, which went in troubles, completely destroyed by in the city center, the CBD, Central Financial District, and the number of fatalities, 185, is a big number. But the good news, if any, is that if it was not because of the first earthquake being at night, where people were sleeping in their own timber houses, well designed, and the capacity design legacy of Park and Pauli and Priestley, the number of victims from that shaking level would have been anywhere in the world in the range of 1,000 to 5,000. I'm not using Haiti, it's not fair. I'm not using countries where the construction was, and I'm referring to Haiti because there are master students who gave a fantastic presentation. Where are you? Cyprien, where are you? Cyprien decided not to come today. He had a great presentation about what you're working with Professor Guerrero. Anyway, the important part was that the city is completely destroyed. If you are alive, your life is destroyed. So the resilience of a community goes through the resilience of the building systems, of the water supply, of the lifelines, and everything else. And the cost was 40 billion New Zealand dollars. Just imagine 40 billion US dollars in Mexico. This is a big number. In New Zealand, it's even a bigger number because it's a 25% of the GDP. But there was a private-public insurance scheme, which I don't have the time to talk about, and allowed things to be reconstructed. So there is a big injection of money to come back to revamp the city. Is basically is not anymore resilient by design, is resilient by injection of resources. So you got impacted significantly, and now we are trying to get back. And obviously, we don't want to reconstruct a city in the same way. We want to reconstruct a city which is safer, not safe, safer, relatively safe. The word safe has been banned by any engineering report Because if you write safe, you are going to go to jail, I can tell you. Unfortunately, you don't want to write, this is a safe building. This is a safer building than a certain threshold that you're going to tell me. This is a most likely than not to be safe. And resilient community means that I would like to avoid in the next earthquake such a big impact to my building, lifeline, society, community, in the whole country. This curve can represent a supply chain, a stakeholder type of asset, we say supply chain, can be a community, can be a building, can be an asset, can be whatever you prefer. Then you put them together, you look at the resilience of a city. The best way to avoid this big area to be there, and the bigger the area, the less the resilience, the best way is actually to minimize the impact, which is, from the beginning, take a punch, but don't go down. Numbers that we've been using and building the financial approaches to present a big national plan of seismic risk reduction in Italy. The only way to convince people, I'm recorded, I'm happy to be recorded for that, is not minimizing the victims in an earthquake. It's very sad to say, but this will not be the reason for which people are going to implement seismic risk. A good, better way to implement seismic risk is we are going to save a lot of money. You are going to be richer. Okay, I got it. It's not we are going to save money, but your salary is going to increase in the future because we will be able to increase your salary because our debt will be reduced. So for how much absurd it looks like, it's about money. If you don't want to use money, use CO2 and direct energy, which is money equivalent nowadays. It's like one of those digital coins, right? Crypto coins. If you're talking about CO2 coin or energy coin, in the Kyoto Protocol back in the ages, they were actually discussing about taxing CO2 emissions, which will come. It was just silent for a while. So if you were not talking about seismic risk, but you were talking the different parameter, the engineering demand parameter or the financial parameter, which is money, which means social impact. Because if you impact economically someone, you're impacting socially. So it is a social, economical, social impact. And if you explain losses after an earthquake in a social, economical, social again, then people are going to listen, which is fair enough, because it's all about people. In that case, I take it. It's all about people which are thinking that their earthquake building is an earthquake proof. And you're going to, unfortunately, surprise them by saying, let me explain your car. Your building car looks like there's a structure behind your panel, which is behind your dress, which is going to be in a specific place, or in a specific place, is completely damaged, plastic hinges. But also there's something else. Don't talk about the flooring system and diaphragm to stakeholders or to the client. They don't get it. Just tell that their new parquet, the new pavement, the very, very fancy wooden floor is going to be completely damaged. By spend 50 to 70 euros per square meter, it's going to be lost. So talk about things, real things. So whatever you have on your flooring system, because of the beam elongation, the beam is going to breathe in the way that we were showing before, is well known that it's going to push and it's going to break. So there is no such as a rigid floor solution. What about what we call non-structural elements? We cannot talk non-structural elements to people. We have to talk about the dress. What about the dress? That facade, the facade is going to break. The facade is going to break, and unfortunately, we did not remember in the course to think about it. The facade can collapse out of plane. Sorry, I'm mixing engineering with the normal language. The facade is going to collapse and potentially can threaten the life of people. So we did not think, engineering terms, that non-structural elements could be a life safety issue. If this is a life safety issue, all you new generation with us should be designing a building to go through life safety assurance, even for the non-structural elements. So the non-structural elements should be designed and assessed against the design level of earthquake, which we have never done before. So bad news. Partitions, the light partitions, can be broken for a very small level of displacement or drift. 0.3%, 0.5, every code is mentioning 0.5. The magic number is 0.5% is going to give you a partition damage. But actually, some of them are going to break at 0.2, 0.3%. And the level of earthquake which takes to move your building to that level of damage is very tiny. So it is very likely that you're going to, it's more likely that you're going to get an earthquake strong enough or not too weak to damage your partition. And you can say, who cares? The answer is, do you know how much does it cost to fix them? Thousands. And you know that in the loss modeling approach has been mentioned, Professor Miranda and so forth and many others, that the cost of the envelope, the dress of a building is actually potentially 75-80% of the cost of the total building. People don't think about it, but I can tell you, if you're telling anyone that it would be idiotic to dress like in a ceremony for a wedding and then to just go and play rugby in New Zealand and football somewhere else in the world, they will say, of course I will not be dressing in a ceremony way and doing. So why are you dressing a building with a new energy efficiency dress and you're spending my money and then you're going to play rugby or you're going to have a tackle on the muddy field? And that's the absurdity of what that's priority prejudice for climate change, which we totally agree, has been forgetting about the priority of fixing the skeleton first and then putting the dress after. So, the new building, designed according to any code in the world, the new design building that you have been taught by us to design as a minimum by law, is going to also have facades, heavy precast facades, which can collapse and kill people. So this is something that people did not know. And people, not only they didn't know, but they didn't know anything about this matrix, which I don't want to revamp, but you well know, apart from some glazing guys over there saying, what is that? So this is the starting of performance-based design, Structural Engineering Association document, Vision 2000, in 1995, mid-90s. The idea was, what will happen in the 2000? For those of you who are not millennials, but are boomers, the 2000 was actually a big thing. In the 2000, the world will go crazy because there were no 4 digits in the computer. There were only 2. How will the computer? So we were expecting the whole computer system to go crazy. But just to go back to reality, it was already prepared. That is something the world has been followed. A 4-level damage states. Fully operational life safety and damage near collapse have been changing depending on the cause in the world. For example, this is often called operational, this is often called damage control, and this stays life safety everywhere, and this instead of near collapse is called collapse prevention. But basically saying small earthquake, small damage, bigger earthquake, bigger damage, and when you get to the design level of earthquake, your building will be this one here. These are pictures from real buildings who suffered that level of damage, which are the reality show of this. Well known. But honestly, this is clear, but people don't know. When you try to explain, they are getting lost in what is this? It's a pushover, and we love as engineers to just get lost our client into what a pushover is, isn't it? So they just don't understand us, and so I say, hold on, son. I'm going to design your house because I'm a brilliant engineer, and the house after the earthquake will look brilliantly like that. If not fired only, I will be aggressively insulted by the client. So there is a missing link. We did not explain that to people. But the missing link is that when you are going to explain to people what the code is about, and I do know that today, your Mexican new code, NTC 2020, I did study, the NTC 2020, which interestingly enough is like the NTC 2019 in Italy as a name. For us, NTC means Norma Tecnica delle Costruzioni, which you understand. For you means what it means. The PC is, I forgot about it, excuse me. But it's basically interesting that we are using, we are developing new codes as we understand our knowledge is growing. But the reality is that the code, people should know that is the minimum by law. If you don't respect the code, you are going to give, is not the earthquake alarm? No, I guess. I would have expected a much low frequency sound repeated every few seconds. With 45 seconds, I could have made hundreds of slides in 40 seconds and then 5 seconds to run out. So the very important part is people are really convinced that we should be using the code as a target. And we're trying to say, no, this is the minimum by law. It's like if you were saying that a car, the minimum by law is a wheel, four tires, a wheel, and it should be able to go through, you understand that. Warrant of fitness is something very clear. But what is the warrant of fitness for our existing buildings? It's a assessment procedure which is written in the code. Let's call it warrant of fitness. And so let's explain that. A new building will not be what you thought, my dear person that I'm talking to, is not going to be earthquake-proof. Earthquake-proof means bulletproof. There is an earthquake, I get shaken, and then I just continue because it's earthquake-proof, it's bulletproof. It's actually different. It's earthquake resist. It's going to be like a car. So this is actually a big, big deal because people are looking for earthquake-proof, and so now it's this part of the 10 minutes. Otherwise, my flight is going to leave without me. This is going to be what the discussion wants to be about, and we managed to discuss about this target, pushing raising the bar of performance by pushing our behavior here. Means big earthquake, small earthquake, a big earthquake should give me no damage whatsoever at the beginning, no damage whatsoever, like wind should not be giving me damage. If a big earthquake is coming, I should still be under the repairability threshold. Do we know how to define repairability? No, but at least we know that we don't know. We need to find a way to define repairability, because if we are able to define repairability using engineering terminology, strain, cumulative strain, number of cycles that it can take, the energy, cumulative energy, and you go back to the Park and Ang, ductility and cycles combined. So you go back to the 1980s and so forth to understand that there was already a concept of, you go back to Bertero and Wang to look at the energy approach. So there is something which has been there in the brain of many great brains to try to define something which was telling better what is the damage than just a maximum drift of ductility. But the real point is that as soon as I tell you that we should be pushing that back, you non-technical person will say, of course you can do it. How much will it cost? It will be like a bunker that you're designing for a nuclear attack, for missile attack, and it's going to be just non-economic, so it's not possible. Good news, it is possible. How does it look like? Now, I cannot believe it, that in New Zealand, sorry, you would not believe it, that when we had the earthquake in New Zealand, the Christchurch Women Hospital, designed in 2007, was the only base-isolated building in Christchurch. I'm talking about New Zealand, Park and Pauline Priestley. I'm talking about Bill Robinson, Ivan Skinner developing the lead rubber bearing, and yet in that country, buildings were well designed for plastic hinges, let's say, because that was done. But in terms of base isolation, there was one only in the city. When the great friends from Japan came to help us in New Zealand, they were asking us to pass on the data of the building monitored that we had. We were just silent. And they were trying to explain again, thinking that it was a matter of Japanese broken English against Italian broken English, not matching. And I was thinking, no, I'm embarrassed because we have none. What do you mean you don't have buildings being monitored? And so I was trying to reply as a citizen, do you know how much does it cost to monitor a building? I was embarrassed. After the earthquake in New Zealand, and after what happened, you, of course, will imagine that we would have monitored everything. No way. Why should I bother? Why should I really bother to put something in? Now the earthquake has passed. Why should I monitor the building? If the building is behaving properly, I do not need to monitor. If it behaves improperly, it's too late. So I don't want to talk about that. I want to talk about this, which is another way of doing base isolation. And it comes from the Greeks, and it comes from the Persians, it comes from the Aztec, and it comes from the pyramids. It's basically, they were able to resist earthquakes by using rocks, blocks on blocks, doing this type of things, which is rocking on the top of each other. This is one of the most well-conserved Doric temple from the Greek, 5th century before Christ, in the ancient agora in Athens. And they were really able to withstand the earthquake, which we did not create. The earthquake had been there much before us, obviously. It's a joke because people think that we are suddenly, in the new world, getting more earthquakes. I heard everything. The climate change is causing more. There are things happening which are weird. I mean, to a point, let's just be realistic. The people had to find a way in our ancestors to deal with that. So this is my thesis where we were working with Professor Macchi in Pavia on the Leaning Tower of Pisa. And I was looking in the 1990s at the modeling of these rocking systems, which George Hausner had been developing the theory of, but when it was time to actually make in a real practice, it was more complicated than just a pivot point rocking system. They are not a rigid body. It's like a reinforced concrete. There is a neutral axis. And so if there is a neutral axis, it's a deformable body rocking. So you need to do things. And you would know that there are ways that people have been doing, using, for example, in Greek temples, to basically allow the temple to slide on the top of charcoals and furs, or to rock. These sliders are our normal, new way of implementing space isolation. They already had this concept. They couldn't go to do anything better than sliding or rocking, because you have a rock. What was the energy dissipation? Forget about it. Is a friction or just damping by contact. So a new interesting development, which is basically a revolution approach in a milestone in earthquake engineering, happened in California, and I want to go there talking about immediately the PRESS program. It was a marvelous, almost by chance, I should say, program that was pushing to find solutions for precast concrete. While marvelous, because it became a solution of rocking elements, being able to develop the temple, Greek temple approach with tendons, giving you a control because you're pushing, you have an unbonded tendon, which is a tie down, and these unbonded tendons allow you to go back and forth. So it's actually a recentering spring. While you're moving, you're using steel rebar or plates or anything, which I don't want to call dissipators here, because otherwise, if I call devices, you're going to think about something complex. They are a piece of steel. And steel likes to be plastic, go in the plastic domain. So it's a matter of shaping to have a more flexural than shear type of behavior, and you can put anything in that things. The pioneer of that, Nigel Priestley, was the coordinator of the project, and I say the pioneer team in a way was Nigel Priestley together with John Stanton, Professor John Stanton of the University of Washington, who at the NIST, National Institute of Standard Technology, in the 90s, was working on some beam column joints with post-tension. A great member of the team was Susie Nakaki. Susie Nakaki was a great designer in the Los Angeles area, which was called in. But there was the whole country in US under the PCI, Precast Concrete Institute, working on that. And I'm strongly recommending to read this book, especially if you're a millennial. So if you did not have the honor, or even if you had, but please to meet in person Nigel Priestley, this is a book which has been prepared by the people who have been mentored by Nigel Priestley. So former students, moving up in the world in different environments, mostly academic, engineering, and so forth, and writing technical stories about the lessons learned under the mentorship or the development of Nigel Priestley, which, just going back to the point, ended up this massive project in the United States developing the Greek temple in the new way. This is a Greek temple which, instead of breaking back and forth, like you would be doing in an emulative approach, is actually rocking back and forth. But it's not only rocking, it's rocking, and while you rock, there is a tie down which is going to control your rocking, and while you lift up, there is somehow a way of dissipating energy, which is cheap and nasty. I shouldn't say nasty, it's cheap and cheap. It's cheap and efficient. And is there any contractor here or precaster? No. So then we can go home, honestly. I can take my flight because it's a pleasure to meet you guys, but we are always preaching to the converted. There's no point of talking to engineers and instead talking about an hysteresis rule if then it's not going to be implemented, because either someone will not believe that it can be done, or someone will say that it's too complicated, or someone will, and I saw these trends, excuse me here, will talk about devices. If I say that it's a device, no, it's not a device. It's a piece of steel. It's the same piece of steel. Allow me that you're using reinforced concrete. Do you call your rebars in reinforced concrete, your grade something, 300, 400, 500, do you call them devices? No. What do? They give you strength, they yield, and they give you dissipation, right? Do you call them devices? So don't call devices anything which is cheap and nasty, okay? Just say it's a piece of plate, which I will obviously test properly. Are the rebar that you're using in reinforced concrete quality control? Of course. Are they able to give the FY that you want? Of course. So let's be very careful in not making things overstated, while this will mean troubles for the design itself. I go to show buildings, and I need to go fast. We were able in the 1960s, thanks to the capacity design principle, to make a big jump, a big paradigm shift. Buildings were not collapsing anymore. We are now in the position of having basic knowledge to avoid collapse of buildings in the new design of any code in the world. So buildings are not anymore doing pancaking in the new codes, and are developing a marvelous plastic angialdehyde. Now in 2020, we're saying, great, what is the next level up? People don't want to have a car, a building completely destroyed and a city completely destroyed because they have one life. Could you please, dear earthquake engineer, deliver to me what I thought it would have been possible, which is something similar to the earthquake proof, and this is getting there, not there, it's getting there. It is going to be something which is going to be a low damage, that's how we call them, a low damage technology. The next step up that we did from San Diego, moving around the Italy first and then back to New Zealand, by the way, is not clear because it's few years later, obviously. But that tall guy is me those 25 years ago and 25 kg ago. Kg means kilograms ago. So I was landed same tall. There was a political mistake. They said, send Italian guys to the building to pretend to mark the cracks that we're taking a picture. If you see, you can see here, there's no safety things, okay? And the Italian guys just went up very happy to be taken a picture for. But I told them, if that was the intention, you don't want to take a 2 meters tall person because the building will look, this building is actually massively big, okay? It was in the lab. So going fast and quick, what was the next step that we developed? And that was in New Zealand. We developed the weakest link of the chain, the Tom Pauli weakest link of the chain, to become as much as possible repairable. And here it is. This is my students from Structural Design 101. Casting, caging, testing, beam column joint belonging to the pre-70. Structural Design 101. Then they're casting, testing, and caging, casting, testing, beam column joint with a plastic hinge. We are 2004. Then they are being taught what for them was nothing new, because I've been taught at school in the concrete course, so it's normal, right? The whole school in the world will be taught the same thing. And they are caging, constructing, and testing, rocking temples with the post-tensioning. And they're developing the understanding that this is easy, and actually can do my design half a calculation, because I understand the rotations here, displacement gap divided by heights. There's a gap opening, but I don't really see the curvature there. This curvature is not something that, if I was going to ask you, what is your strain right now? See, what question is it? Okay, what is your weight? Quanto pesi? You know it. So you should be able to calculate your strain, your axial strain, right? Okay, of course I can, but it's not something that you're right? So the same thing is I know how to calculate the curvature, but I don't see the curvature here, while I can see the rotation. So if you tell me 0.5% of drift, 1% of drift, I immediately understand, like a Lego system, our brain goes back to blocks. Is this going back in terms of complexity? It's the other way around. We are trying to get into an earthquake engineering era, which is so well developed that things are becoming simpler. Because don't tell me that you're so, excuse me, I need to get your help. I will lose the flight. Do you have a mobile phone? Yeah. Really? So you're an electronical engineer? No. Okay, I thought you were. Because people think that in order to be able simply to change this plug and play, which is a fuse that we developed and we didn't make money because I decided not to patent it, such that instead of buying a couple of Greek irons, I was making a joke, I would continue to be a poor academic. So I love to be a poor academic. So these plug and play, which are fuse type, can be architecturally placed anywhere in your building. They are cheap, $15. $15. Don't call them device because they're becoming $1,500. So it's a piece of steel, $15. I can develop with anyone with $15, and I will send you the drawings, okay? If it becomes $20, just because you don't make many, and they are going to be around your house exactly where you want, in the living room. And people are going to look at your thing, and they're going to say, unbelievable. So you really managed to get the MMX 2.0 version S2 Galaxy dissipator. And you say, yes, because I have a good contact in Japan, and so I managed to get one before it went again. The point is that earthquake engineering, this was a joke that I made 20 years ago, and this was the starting point thanks to some architects that believed on, oh, it's a fashion, that this can become fashion in earthquake engineering. So you can make this fashion in your living room. As soon as you make fashion, I don't really care about the fashion. I care about, I want to see it. I want to access it. I want to know that I can change it. Such that after an earthquake, these are First of all, where do you buy them? You go to the supermarket where you have light bulbs, and you just buy, instead of getting watts, 60 watts, you buy the extra small. The watt, are you an electrical engineer when you go to buy a light bulb? No, great, so you can do it. Similarly, you are going to tell to people, you just buy what is, when it is written kilonewton, forget about the kilo, put the kilo. When it's written Newton, oh, Newton, yes, the one of the apple, yes, the one with the apple. You just take a 20 kilonewton. But the big problem of this in the supermarket would have been, where I make a mistake, the attachment. I always make a mistake. It's a type of attachment like this, so we made one attachment. These are the plug and play in place. So one universal attachment, which is basically a slotted connection with double rods. Anyway, design codes. I know that we are losing a flight. So how can you design it? Did you know that it's already been mentioned about this in 2004 in a FAB bulletin, which is not a code. It's a state of art. And that was a brilliant committee where Professor Rodriguez disappeared because he said I have to go. This was Professor Park and Watanabe from Kyoto coordinating a big committee of people, which I had the great pleasure of being part of, and that was actually already implementing the suggestion for something. But then he went in the New Zealand code. 2004, 2006, Bob Park was really keen to have it done. He asked me to write a chapter which became normative. 2006, we had a code which you can use in Mexico. That code can be used in Europe. That code can be used in Latin America, in Japan, in the US, because it's actually following the basic requirements to be provided that evidence based on experimental numerical tests are being done, and provided that you have an internationally recognized code, you could use an alternative solutions. So people could use it. So we managed to get the theory, the explanation in the code. Not sufficiently enough. People were saying, I don't know how to design it. Thank you for telling me that I can do it. But so we prepared a design handbook, which we were discussing with Professor Guerrero. We should be doing a Spanish updated version over here to prepare a design handbook with a full design example. But you don't want to talk about theory, so we have engineers here and engineers at home. So billings, is 39-story building sufficient enough for you? San Francisco, financial district between 3rd and Mission, designed by Professor Bob Engelkirk, who was a great designer and also a joint professor at UC San Diego. To cut it short, this was using the generation 0, so the mild steel inside the bar. But then we managed to go to the probably, I arguably say that's the most conservative country in the world in terms of civil engineering is us, Italy. It's not you. You don't, it's us. So when we presented the first work of the press in Italy, I remember it was a Turin, 1999, Italian Society of Electrical Engineering. There is a young man talking with a name in the list of Calvi Priesti. So they wanted Calvi. You want to have the big man. And there is this guy, tall, so I can't say this, presenting for the first time the experimental test in San Diego. Anyway, people said, which is something they would not have said if it was Nigel Priesti at that time talking or now Michele Calvi talking, they said, these things interesting, because you cannot offend the brain of Nigel Priesti back and so forth. Interesting, but dear Dr. Pampolini, in the land of towers and bell towers and masonry, this is not going to happen. And I say, sure enough, we're going to do it. So 2 years with the office, made it. In 2004, we had the first building. But beauty is that we received a prize. Who from? From New Zealand. You don't want to receive a prize from your own country, do you? Because that building in Italy did not exist. You could not say that this technology did exist because this technology was cheaper. Not nasty, cheaper, higher performance, and how could you just justify that you are not able to deliver? And so we were trying to explain to the precaster that, don't worry, you can do it tomorrow, because it's nothing different. You just prepare a duct, a PVC duct, you just run a tenor, so it's nothing different what you're doing. Oh, if it's nothing different, then I'm not so scared. So it was really a matter of time, but by the time we were trying to convince them, I was in New Zealand since 2002, okay? So we are there, and then we developed, we understand that, Argentina, Costa Rica, and we got to know these buildings in this area thanks to ANIPAC, workshop in Veracruz 2006, where there is an invitation to different places, people around the world to explain what's going on. And I was happy to talk about the press development in the United States, going to Italy and then going to New Zealand. 2006 I was already in New Zealand. And the people over there, they were already showing me that, oh, we have been following this work and we have been actually doing things. New Zealand, this is what we did, plug and play. This is a building in Wellington. This is a building in Christchurch with a U-shaped flexure plate, which is a piece of steel developed by Ivan Skinner in the 1970s. Jim Kelly, Professor Kelly from Berkeley, went to a sabbatical to work with Park and Poly, and they worked also with Jim Kelly, with Ivan Skinner. Anyway, this building itself went through an earthquake. It's nothing different from what a precaster could think about it. There are detailing, which are the most important things. Detailing is saving a building. And after the earthquake in 2011, the building was basically unscathed and went on the news. The city is down. What is that building? Oh, it must be a nuclear bunker. One of those buildings we know that could use a new technology. So they came and interviewed us, and I need to go fast. I have a confidentiality agreement. I could not say how much we saved in terms of money. But I agreed that I would have said, because I couldn't say nothing, that it did not cost any more. So double negative. I will not say how much it cost because we save money. I will say it did not cost any more. But then I tricked a bit. When the people came and they put together the interview, I asked them to go to talk to my mate, colleague, and he was allowed to, because he was not an academic, to say the cost. And so he basically said, oh, we saved out of 7 million, 1 million. And we save money here and there because once you do a base isolated rocking system, it basically is a rocking isolation, you are able to control the level of the detailing in a much better way. What will be the next step up? The next step up is that it's not only the skeleton to be low damage, but we want to have a facade. I need to go fast and quick. A partition, so the full dress, either being heavy or being light, should be following detailing, which we have been developed in 15 to 20 years and testing. In 2014, we tested the new evolution, including clay bricks that can go through a major earthquake higher than the design level one without having damage in the non-structural elements. How much does it cost? Less. Why? Because it's all prefab. Facades coming in, clicking in, plug and play. If you want to change the facade, you can change in the future. Test, detailing. I will give you the slides, don't worry. And there is a, let me see if it goes. So there is a precast columns with a precast beams connected by post-tensioning with top and bottom plug-and-play dissipators. We call them plug-and-play. Please use their name, because the reason for which you have a name is that someone, your parents gave you a name. If it's not patented, at least you use the name that I gave to the baby, okay? So this is just a matter of courtesy. Some people just naughtily change the name pretending it had a patent on it. So this is going through hundreds of earthquakes, 100 earthquakes before we received the media. And the media were actually asking, it was a sort of a challenge. You tell me the earthquake, we run the earthquake. Do you have Kobe, really like a music list? Do you have Kobe? Of course we have Kobe, 1995. Which station? I don't know which station. It's like, just Kobe. Okay, I'll give you a station. And we are running the show. Do you have Mexico City 85? Yeah, but it's not really actually, okay, Mexico. Do you have whatever, Loma Prieta? Do you have, you see the point? And they were watching these things happening, and they were just not getting excited and saying, really, I don't understand. Nothing happens. And we're telling, that's exactly the point. Nothing happens. He's actually shaking. Oh, we were expecting to say big, to see things breaking, explosions. I'm exaggerating. We're thinking, no, that's exactly the point of almost an earthquake-proof building. Nothing is happening. It's shaking, and then at the end of the day, you go back. And that's the zoom in. So just remember your plastic hinge, our plastic hinge, which would develop many cracks in that length. That would be damage. Now, all the cracks are concentrating in a big gap opening. So geometrically, it's the same thing. But air opening and closing means no damage. Obviously, there is a steel protection over here. There are tiny detailing. We don't want to allow spalling of the concrete cover. The cover concrete should not spalled. Why did we study that the cover concrete will be spalled? Because we did not think about the protection. Why we do not think about the protection? Because we thought that this is the acceptance of damage that we should be receiving. Dissipators on the top and the bottom. I said dissipators, excuse me. Plug and play piece of steel, so the bottom and the bottom. And then you put on the facade. This is really complicated once you think about it, and it's very simple, the solution. It's a matter of tuning The rod that you're connecting through is a matter of allowing the movement to happen. Once you know the solution, it's extremely simple. And the earthquake, concentrate on that. This is a very heavy facade, which typically will collapse. But if you're allowing the detailing to allow for the movement, so it's a sort of a kind of slotted connection, drift-based, this is able to go back and forth, 2% of drift, 3% of drift, 4% of drift. We can design the dress to be like this. It's basically the same concept of a slotted, bolted connection where I'm not breaking because I have the movement allowed in my things. And from underneath, this is the facade connected with a U-shaped flexural plate, a piece of steel bent, which costs literally a few dollars, underneath the beam. And again, the facade is moving. While it's moving, it's also dissipating, so the movement is released. So why not in timber? I go through. We develop in timber. Did you, sorry, I keep on looking at you. You need to help me. Do you have a book on pre-stressed concrete, don't you? No, really. You're an engineer? Okay, I need an engineer. Do you have a book on pre-stressed concrete? Of course. Near the book of pre-stressed concrete, do you have the book of pre-stressed timber? Why? Because you thought it did not exist. That's why we are crazy enough that we created pre-stressed timber. Once you start looking at this, it was just happening as a game. It really did happen. Things are happening by chance. We were using wood models to test, to explain to the students that things are moving. And then a new type of wood came into the lab, which is a laminated timber, micro-laminated, 3 millimeters veneer, laminated veneer lumber. And basically we said, what is that type of timber? Oh, it's a new thing, which is able to give you in compression 47 megapascal. So if I use a rocking tempus, which is relying upon concrete only, I need to go, the flight is leaving. Fast, test in the lab. We are not going to break it. So basically I could stay here half an hour to show you that we were in the lab pushing back and forth. We were not able to break a timber post-tension. We call it pre-stress, but because it's press lam, timber building. We test the big things. We make a big major project. We are also, after New Zealand, we are doing things in Europe. You look and check this guy, and I'll show you. Sorry, it's not working. This is supposed to be working if I hold on a second. We managed to do buildings in New Zealand, coming back to Europe. The European people are starting from scratch. All this can be done only in New Zealand, only in Japan, only on Mars, only on the moon, so not in Europe, because we are say, oh, I already listened to that, don't worry. We get a project, we managed to construct the things, we managed to put on the shaking table in Lisbon, and this is going through an earthquake, which is basically a collapse prevention earthquake. The building should be collapsing. You test the building, it's shaking as it should be, displacement-based design, you check the drift, and the building is unscathed. And underneath the building, in the building, Hector, I know that I'm putting pressure on the driver now, and on the, I want to show you the internal, which is coming. There it is. This is masonry, constructed in a slightly different way, using just C-channel to allow for the rocking to happen. So you're just allowing not to have a shear crack, but to have a little bit of movement, so you anyone can construct them. Glazing, if you check despite the glazing, you design a slot, tiny detailing, which costs nothing. You need to know what you're doing. Glazing does break, which is incredible. Masonry doesn't break, 2% of drift, under collapse prevention earthquake. And so, how did we build the city? This is the plan. This is the plan, beautiful rendering, and these are the real buildings. Concrete, timber, steel, concrete, timber, combination of the material in a low damage perspective. Base isolation, viscous temper, combination of K-braces with replaceable hinges. There is basically a lab of evidences of earthquake engineering in New Zealand. So if you get some money, now the flights are expensive, but just get there because this will be the most impressive for you laboratory of earthquake engineering of a reconstruction of a city. So these are real buildings that we had in Wellington before the earthquake. The earthquake was in Christchurch, but then in Wellington we got earthquakes happening too after the 2016 one. Anyway, there is a construction site with the plug-and-play, construction site already shown you, building with the plug-and-play devices in the police station. They wanted to see them because they wanted to express the architecture. Timber, real buildings, the first one in the world. If I was going to show you this in gray, in black and white, you would think it would concrete. I really need to finish. There are plenty. I will show you so many that basically people have been used to. This is like a smartphone. do you still, if I was going to give you, I go to the last one. So you see, I will give you all the references. But I want to go to the last slide. This is a new library that we designed and constructed a few years ago, displacement-based, the whole thing. You look at these walls. It's something that anyone can do if you know what to do. But I want to go to the last slide, which is this one here. Do you monitor your car? Of course I do. Do you monitor a billing? No, we don't. Why don't we? So we started monitoring billings as per, I don't sell you a car without the basics of the information. I don't give you one of these billings without the base. And it's not because the billings is not good, but because you need to know what's going on. So performance, how much did it cost? It improved, the cost went lower. How much did it cost? The price went lower. So improvement of performance and low cost, same thing in building. But let me tell you, I will not tell you how much does it cost. I will tell you it will not cost more. But it's actually just an improvement of performance. So would you buy the Motorola 9080? No. Would you buy the IBM 9084 build computer? You must be crazy. Would you buy the 9080 billing system? Oh, of course not. I'm not that, and I'm stopping here. It's called no-brainer. But the only reason for which you're not going to buy anything all over is because you know about them. The reason for which we don't know about this, we don't buy because we don't know. So it's just a matter of we don't know. These are mathematics, that's where we have been working on an exoskeleton to retrofit billings from a sustainability, seismic, and energy efficiency point of view, and you are going to get all the benefits. I'm finishing off. I need to say thanks to many people who have been part of all this journey, and these specifically are the people coming from different parts of the world to help us, in addition to the victims, like Tom Poli was tend to say, the research victims. And thanks for your attention. Kia ora, which is New Zealand. I need to run away. Grazie per l'attenzione. I'm very sorry for having to rush off. Thank you.
Thank you, Professor Pampanini, for this great presentation. No tenemos tiempo para preguntas, mil disculpas, pero bueno, ahí está el correo si alguien quiere información, o escríbanme a mí, con mucho gusto les mando más información. Pues que tengan linda tarde. Buenas noches a todos, muchas gracias.